Units 1, 2, and 3 were kind of our introduction into functions to make sure that all of our phones, laptops, and whatnot are put up right now. Okay. We are going to start, I would say, the groundwork that will be required in order for us to start these. What we are covering today. And I know you like hear this a lot, and so there's like a tendency to dismiss this statement, but I mean this very, very literally. Everything that we are going to be covering today is incredibly essential to your ability to understand what is going on for the next rest of those. Unit 4 is all about trade. Unit 5 is properties of trade, and Unit 6 is applications of trade. And so if we don't know the unit circle information by the time we get through Unit 6, I'm going to have very, very little patience with that. This is really something that I need us to kind of have down within like the very, very beginning. To that end, we are going to be having a unit circle quiz the Wednesday we get back from break, which I know is a fairly fast turnaround. But what that is going to look like is I am going to give you guys like one quadrant of the unit circle to fill out 20 blanks. So it'll be out of 20, and you can retake that quiz as many times as you like until you're happy with your grade. If you get a 19 out of 20 and you really want a 100, then great, you can retake it again. That's totally fine. And we'll do like once the start of class for a week, and if you still want to retake it after that, then you can continue to do so. But my assumption after Wednesday, after the quiz on Wednesday, is that we all perfectly know the unit circle, and I'm going to be operating under that assumption, independent of the fact that I know it's not true. So that is my expectation. I realize that that might not be reality, but I need to continue moving forward like it is reality. And so then it is on you guys to make sure that that we are keeping up and that is really very much locked in. What we're going to do today, though, is we are going to be very, very thoroughly going through this. Hopefully in such a way that you are not having to memorize every single feature of what we are going to be talking about. My claim, or the framework that I'm going to try to give you, will require you to memorize a fourth of the information. And then from there, there are a lot of patterns that we can use that will very quickly kind of fill in the rest of it. So that's what my goal is to kind of give us both the patterns and the kind of baseline information that we are going to be working with to all kind of fit into, I would say, this kind of like underlying system for which we are going to be doing our trig stuff. All right, so first and foremost, what is the unit circle? You hear this a lot, not even necessarily in the context of trig. This is just like the unit sphere, the unit circle, often mentioned in kind of a variety of different contexts. But very, very simply, this is a circle with a designated radius. In particular, this is the circle centered at the origin with a radius of 1. We're going to see that radius of 1 is really the important thing, the important piece of information that we're going to use, and that's how we're going to really derive a lot of the information that we will see from our circle here. Now, for the unit circle, there are two kind of main components that we can talk about, and what our trig functions are going to do is they're going to really allow us to exchange that information. They'll take us from one kind of way to talk about a feature of the unit circle to another. We can talk both about the angle of rotation that we would find. So for instance, what is going on if I rotate by 60 degrees, or what's going on if I rotate by 143 degrees, something like that. As well as the XY information that such a rotation is going to give me. We're going to first focus on the rotational information, and then we're going to connect the rotational information to XY information, like on the actuals. All right. Starting off, when we are talking about the unit circle, we are always going to be starting in the positive X direction. So this point right here, in fact, what is this point? Well, this is the origin. So what would this point be? 1, 0, right? 1, we're radius of 1. So 1 in the X direction, 0 in the Y direction. This would be the point 1, 0. And how much have I rotated if I am starting here? How much have I rotated in order to get to this point? I would say like 0 degrees. Or how else could I get there? There are actually a lot of ways that we could get there. 0 degrees is 1. Or what else? How else could I get to the starting point? Yeah, I could do 360 degrees, right? So we will find that our kind of circle, the image of our circle repeats every time we rotate once all the way around the circle. And so a 0 degree rotation takes us to the exact same place as a 360 degree rotation. Does that mean that a 0 degree rotation and a 360 degree rotation are the same? No, they mean different things. This tells us we don't move at all. This tells us we rotate once. But as far as like the on the unit circle information that they encode for, they give us the same X and Y value, in particular an X value of 1 and a Y value of 0. So, okay, there aren't enough blanks on the unit circle that I gave you. I would do like a 0 degrees above it and then a 360 degrees below it, just kind of like underneath the blank for the 0 degrees. That the other blank that's next to the 0 degrees is going to be filled in with something else. We're going to see what that is in just one moment. And then the point that we have the coordinate pair x, y values. Okay, so if a full rotation is 360 degrees, what would halfway around my circle represent? 180 degrees. Like a 180, turning a 180 is completely reversing directions. So that would be a 180 degree rotation. And what would the coordinate be on this side of my circle? Yeah, -1, 0. Okay, what would my quarter rotation be? That would be 90 degrees. Okay, what would the XY information be here? -90 degrees, and we said 0, 1. 0 in the X direction. Always going to be, we always need to make sure we're going to be within a distance of 1. We're never going to see larger values than that. So 90 degrees, 0, 1. And then what would our 3/4 rotation be? That would be 270 degrees. And what is our XY coordinate going to be there? 0, -1. Very good. Yeah, so when we are, good point here that I forgot to mention. So we're always starting in the positive X direction. And then the kind of standard way that we're going to rotate is we're going to rotate counterclockwise through the different quadrants. So think of this as quadrant 1, quadrant 2, quadrant 3, quadrant 4, and we're moving through them as we rotate in this counterclockwise clockwise direction. There will be times when we rotate clockwise, we will see that that is indicated in a special way. We'll put a pin in that and we'll get to that after we get back. But for now, yeah, kind of standard direction of rotation, counterclockwise. Starting positive X, rotating counterclockwise. These are called the quaternal angles, just because they kind of form the boundaries. It's not like vocab that I need you to know, but that's cool. They have a special name. There you go. Okay, pausing here. Questions on kind of our broad scheme setup or what we're trying to do here. Hello. Join the fun. We've established the quaternals, which is just the 0 degrees, 90, 180, 270, and then back to 350 by the end with the points that you see kind of described here, rotating them. Feeling good? Not too bad? No. Okay. Make it a little worse. Not too much worse. Not too much worse. Yeah, we'll we have been using degrees to measure angles basically forever. Like when you do angle measures in elementary school, when you do angle measures in geometry, all of that is referring to, like, you refer to degrees. And we think about like what a degree is kind of trying to tell us. One, they're kind of arbitrary, like why is 360 degrees a full rotation? I'm sure there are reasons for that, but kind of like, you know, Fahrenheit and other metric systems, not super objective. And also one that we are going to find doesn't necessarily, kind of requires a little bit of extra thought, even though it's a little bit more intuitive for us. So nothing wrong with using degrees here. I kind of think of degrees as kind of talking about the hinge action of thinking about like, okay, if I'm rotating by a certain amount, like if I think about like my clock hand rotating a certain amount, the degrees talk about what the hinge is doing, but I don't have to just focus on what the hinge is doing. If I'm rotating by 90 degrees, I could also think about, for instance, the distance that I would have to travel to arrive at where I'm kind of ending up after this 90 degree rotation. So we can talk about degrees and that's fine. We could also talk about this, what we would call the arc length that we would have to follow to adhere to this 90 degree rotation. And that's actually the more standardized form of angle measure that we are going to talk about. And that is called a radian. So the radian, or kind of the radian measure, this is going to be we're going to say the angle measure presented as a distance traveled around the unit circle. I think that's an okay way. So here we're talking about tracing out a distance, tracing out this kind of arc length, rather than like this hinge action of like opening by 75. Ultimately, we'll see that we can translate pretty easily between the two. Again, that'll be something that we do when we get back. But for now, this is kind of a good spot to be. If I'm tracing the outside of my circle, what is that feature of my circle that I'm basically measuring? We're tracing, yeah, we're going to be tracing around the circumference of our circle by the time I do a full rotation. So one full rotation basically gives me one circumference of my unit circle. good ACT review for what we have on the Tuesday that we get back. What is our formula for the circumference of a circle? That's area of a circle. So circumference here. This is way back, is 2 pi r. But on the unit circle, what did we say our value of r is? But on the unit circle, our radius is just 1. And so the circumference of our unit circle is just going to be 2 pi. So how much distance do I travel if I start here and rotate all the way around my circle, finish here? Well, I've traveled 1 full circumference, which we said is a distance of 2 pi radians. Or if we traveled none at all, we could say we've traveled 0 radians. That would take us to the final stopping point. So 2 pi radians representing the full circumference that we can go along the unit. Okay, if 2 pi represents a full rotation, what would a half rotation be? That would be pi. Okay. Well, we could think if pi is a half rotation, what would a quarter rotation be? We could also do this. If 2 pi is a full rotation, what would a quarter rotation be? Yeah, 1/2 pi, you'll often see this written as pi over 2. Think of this as like 2 pi divided by 4, but then I'm simplifying that to, pi over 2. All right, cool. And then what would 3/4 of the way around my circle be? Yeah, but a little bit cumbersome to think about it that way. You'll often see this written as 3 pi over 2. So again, thinking here, if I take 3/4 of 2 pi, I get 6 pi over 4, which simplifies down to 3 pi. And this kind of framework of thinking about like what fraction of my circle have I rotated around, super, super, super convenient. And actually is how I'm going to find the radian measures for every single angle that we're. And it's also how we would really easily convert between degrees and radians. Again, something that we'll look at later. But if we can figure out what fraction of a circle an angle measure represents, we can very quickly figure out what the other angle is supposed to be. That other measure. Which is a little bit different, I think, than how it's normally presented, but I like my way. Nice and intuitive, and we'll see it works for more than just angle. All right, so questions here with our quaternal angles, now in radians, with all the x, y. Yeah, there's like a multiplication factor that most people teach. I prefer to think about it as think of what fraction of the circle that angle measure represents, and then convert it into the other by just multiplying by what a whole circle rotation. So for instance, and we're about to do that. We'll see that in action here in just a second. Okay. Yeah, so but then that we'll look at it more specifically also on Monday when we get back from break. But we will do a little bit of that here in just a second. Which is a nice kind of framework, and it works well for arc length and works well for sector area, and it's just a super convenient way to think of things. Yeah.
So for the 180, would you just do 1/2 times 2?
Exactly. So a halfway rotation around the circle, you would do 1/2 times 2 pi, which is where the pi is coming from. Exactly. Exactly. Nice. Okay, so those are good to know. Kind of keep those tucked away in your back pocket. They'll also be good to know to kind of help us understand what quadrant we are in. So for instance, if I am in between 0 radians and 2 pi radians, then the implication there is that I am in quadrant 1. Why do I care about being in quadrant 1? Well, what's maybe different about values of x and y in quadrant 1 relative to my other quadrants that we see here? We're going to have positive x's and positive y's as long as we are in quadrant 1. What if I'm in, well, we'll just go through. What if I'm in quadrant 2 here? Negative x's, positive y's. Okay, what about if I'm in quadrant 3 here? Both will be negative. And in quadrant 4, positive x, negative y. Okay. Oh, keep that in mind. That's okay. So quaternal angles, great. Now we are going to do the actual, like the memorization component that we need to know. I will say this all comes from facts that you guys already know, or should hopefully already know from geometry. If you don't already know them, this will be a really good reminder. Again, they show up a lot on the CT. These kind of ratios that we're going to see here. Yeah.
Do they show up on digital SAT as well?
Presumably.
So pre-calculus and algebra 2 honors are heavily required.
Well, we're going to see that we're just going to go over some geometry facts, and we're going to use those geometry facts in a pre-calculus setup. So this is essentially how far can we run with geometry. A lot, and who's interested in teaching what? I'm guessing that they are. They are separate. I would imagine any math teacher would be able to pretty adequately explain this. Although I'm pretty partial to this. This is one of my favorite lessons. I think that it's really nice that you got, which is cool. All right. So my claim is going to be the claim that I want you. I don't want you to memorize everything. I mean, ultimately, I want you to know it all. I don't want it to be a pure memorization. I don't want it to be, okay, you're trying to remember, okay, if I'm in this blank, then I'm doing whatever. I want you guys to memorize quadrant 1. And then from quadrant 1, hopefully we'll be able to extrapolate and look at an angle and say, oh, this angle is going to be a quadrant 2 angle. That's going to have a similarity to something that's going on in quadrant 1, and then I'm going to have to adjust it because it's in quadrant 2. And hopefully that process is a lot more organic than just, okay, I know exactly every single data point that is along the circle. 2 special case triangles that we are going to know. Okay, we're talking about circles, and now he's bringing triangles into this. What on earth is going on? Well, let's say, for instance, that I want to understand what's going on after a 30-degree rotation, what my XY information is going to be. So on my circle, what if I rotate by 30 degrees? And what we're going to find is that the Y information corresponds to the opposite side of this triangle that we can draw. And our X information corresponds to the adjacent side of the triangle that we can draw. Okay, and so whenever we're asking about a particular point, it's actually a triangle, right? The thing that we're actually trying to kind of get after is this point here, which we can arrive at by this kind of triangular motion rather than going straight. So 2 triangles that we need to understand, that we need to discuss. One of them is going to be a 30, 60, 90 triangle. And the other is going to be a 45, 45, 90 triangle. Okay.
So do we do the 30?
We're about to do it here. If you wanted to fill this in on the back, you can, but it's going to be Federal city. Okay, so for our 30, 60, 90 special case right triangle, does anyone remember what the ratio of sides is for a triangle like this?
For 45, I do remember for 45.
Okay, what's it for, sure, we can fill that in. What would it be for 45, 45, 90?
1,
Yeah, I like that framing. I'm gonna phrase it as x to x
the X squared.
to x root two. But 1 to square root two is also right.
And then for 30, 60, 90, it's X, 2X,
Which one's 2x?
60. No, 90 is 2X.
90 is 2x.
And then 60 is X to the power 2. X times the root of 2.
X times the square root.
Of 3. Sorry.
Yeah. Okay, that's just like good triangle facts, again, to kind of keep in your back pocket, or I don't know, like the ACT that you have when you come back after break on Tuesday. This kind of thing. Okay, sure. All right, let's try and take this and see if we can't figure out what it's going to say specifically when we are on the unit circle. So we said for our 30, 60, 90 triangle, that the side opposite 30, so the short side here was going to be x, the hypotenuse was going to be 2x, and the length here was going to be x root 3. So x, 2x, x root 3. What additional piece of information could I use in order to actually figure out what this value of x is? What is my missing value? How can I? That's going to be the right. So what feature of my triangle here is equivalent to the radius of my unit circle? It's the hypotenuse, right? This 2x value is the same as the radius. And on my unit circle, what is my radius? That's always just going to be 1. If 2x, my hypotenuse, is 1, what is my short end x going to be? 1/2. And what is x times the square root of 3 going to be?
2 times square root of 3.
Sure, or root 3 over 2.
Oh, that's
Okay. Long side here, if this is my origin and this is the point that I'm after, which side represents the x value, which side represents the y value? Kind of confusing because I used x's here, maybe I should have used a different variable. But in this case, is it the length or the height that's going to give us the x value? The length is going to be the x, and the height, this 1/2 here, is going to be our y. This is the point said for 30 degrees. This was the point, root 3 over 2, the length to a height of 1/2. And then tie it into this. Before, very soon. Wednesday. But that is ultimately why we need to know this is being methodical. But also we'll find that it's pretty easy once we understand what trig functions are actually. Yeah, first one's 30 degrees. That's kind of the first relevant one. Okay. So that's our degree measure. That's our XY value. Let's talk about the radian measure. 30 degrees is how far around my circle? What fraction of my circle is a 30-degree rotation?
112.
1/12 of the way around our circle. How'd you do that, Abhi? Yeah, or 30 out of the 360. Yeah, to get that it is 1/12 of our circle. So here we said 30 out of 360 is 1/12. And so if I want that to be in radians, what is 1/12 of our full rotation 2 pi? 2 pi over 12 or pi over 6. So the radian measure that we will see associated with 30 degrees is actually going to be pi over 6. Yeah.
So for 180, you have pi. For 90 degrees, you have pi over 2. So if it's a 90-degree rotation, what does pi over 2 stand for?
Pi over 2 is the distance that you travel along the circumference to do a 90-degree rotation. But it's just another way of characterizing a rotation. It just tracks it along the edge rather than doing the hinge motion. Yeah. So say again.
Like,
So the radius on our unit circle is defined as the distance from the center to the edge. If we're looking at which feature of our triangle is center to edge, it's always the hypotenuse is always going to be center to edge. So the hypotenuse is always fixed at 1. And then for these specific special case triangles, we know that the ratio of sides. In this case, we know that if the hypotenuse is 1, then the short side must be 1/2. And then the longer side must be 3. Okay, so hypotenuse is always 1, just because we're on the unit circle, and you'll notice that the radius is always the hypotenuse when you draw that triangle. If the hypotenuse is 1, and we know that the hypotenuse is double the shortest side, then the shortest side must be 1/2. And if the longer side is the shortest side times the square root of 3, then 1/2 times the square root of 3 makes us that longer side.
but how do you know, like, which?
How do we know like those ratios or like
Yeah,
the table?
Why would you put one in?
Because this distance here is the x distance, and this distance here is the y distance. Does that make a little more sense? Yeah.
Would that be like a bonus question, if, like writing proof on how, those are like the values to get, for 30, 60, 90?
I can do better with bonus questions for our trig. Don't you worry, I'll have great bonus questions for our trig test. Don't even worry about it. They'll be so good. They'll be so good. Yeah. I think someone got one from the Unit 2 test. And several people, I think, got the bonus question. I will say, I haven't looked at your guys' Unit 3 test, but judging from Unit 1, the idea of the burden of proof, what is required to show that something is true, is understandably a little bit lost on us, because unless you had me for Algebra 1, then that is not something that you have seen kind of formalized. Question for you. If I'm trying to prove that it is going to rain every day this week, can I look outside and say it's raining today, therefore it's going to rain every day this week? No. So trying to prove an affirmative with an example isn't enough. Like it shows it for that particular example, but it doesn't prove that it's going to rain for every other value that I could have possibly picked. Now, if I'm trying to disprove that it's going to rain every day this week, could I point outside and say it's not raining today, and would that be sufficient? Yeah, so you can use counterexamples to disprove something, but you can't use an example to prove something. So if you said, oh, look, the ln of 1 minus the ln of 4 is the same as the ln of 1/4, that's true, but it also doesn't prove anything. It proves that it works specifically for the ln of 1/4, but it doesn't prove anything beyond that.
So you use like.
You would need to show it in generic cases with variables, yeah. Don't worry. It was just like people tried to show examples on the bonus question on the test, and that's not enough to actually. Most people.
Yeah, so on the bonus question, I actually had it, but then I didn't have enough time to like write it. So can I have the bonus question? But I don't want.
It was proving the quotient.
Question.
Yeah, proving the quotient.
Okay. I did.
Okay, but that was kind of near nor there. It was mostly just something that I was chuckling to myself while grading the test. Which I was glad that I was able to find humor in it, which meant that the test didn't go that poorly. Which is good. Okay, let's use similar logic. Actually, before we use similar logic for the 45, 45, 90, let's talk about 60 degrees. That's the larger angle that we're gonna see in quadrant 1. What's the difference between a 60-degree angle and a 30-degree angle in terms of our triangle? Yeah.
Oh, I don't know. Is this the middle one or the one?
This is the big. Yeah, I skipped over.
Okay.
Yeah. We're talking now about the one right before 90. It's the same triangle, but I've like flipped it, right? Like a 60, 30, 90 triangle and a 30, 60, 90 triangle. It's the same angles, it's the same ratios, but now my tall end is my Y value and my short end is my X value. And that's all I've done. The difference between the 60 and the 30 is my X and Y have switched. So for 60 degrees, what is my point going to be? Okay, 60 degrees represents what fraction of my circle? Sixth of the way around my circle. What would a sixth of the way around 2 pi be? Pi over 3, 2 pi over 6, simplifying 2 pi over 3. What is 60? How much of a full rotation is 60 degrees? 1/6. Yep. And so what would 1/6 of 2 pi? Pi over 3. Yep.
Or you can just do it.
Or you could do double. Yeah, you could double pi over 3. Either way. Yeah, so the X value is now the short end and the Y value is now the tall end. So it's the 1/2. Good questions. I'm more than happy to pause, and if we have questions, this is where we should catch them, because if we feel good about quadrant 1, then hopefully what we feel for 3, 2, 3, 4. Yeah, same triangle, but I have now like rotated it in a weird way. I've like taken these 2 corners, like traded them. And so now the X value is my short end and the Y value is my tall. So this would be X root 3, and still 2x. Or again, X is just that 1/2.
Why couldn't you just write 2 to the square root of 3? Why is that?
1/2 times the square root of 3. You mean?
Oh. So does the X always go across from the 30?
Yeah, the smallest end is always across from 30. Yep. It's almost like the opposite side of 30. Which we'll see. But that'll be Wednesday of next week. We'll tie it into our trig functions. Good questions. Other questions here? How's it going? Yes, yeah. Mhm. So to get the side length here, we said that the hypotenuse is 2x. Short end is then 1/2. So 2x is equal to 1, short end is equal to 1/2, and 1/2 times. And then to find the radian measure, it's like the fraction of the circle thing. Let's do 45, 45, 90 as well. So we said that this was x, this was x, this was x root 2. Similar logic, what does x root 2 need to equal? This is just equal to 1. And so what is x going to be equal to? Well, for x. How do you solve for x here? Well, x isn't being square rooted, so we don't have to do that. Yeah, just divide it by the square root of 2. 1 over the square root of 2. Okay, that's generally not how it's going to be presented. If you were to write it like that, you get full credit. That's great. That's fine. Fun little math history fact. Old calculators used to not be able to divide by irrational numbers like this. And so you had to rationalize your denominator in order to make it so that the old computers could handle them. New computers don't have an issue with that. So this is no longer like a bad answer. But before, it couldn't really be processed, and you would generally see this written as root 2 over 2. And I'm going to write it as root 2 over 2. It is a bit outdated, the need to do that, but here we go. Okay, x and y value, that information is the same.
Can you get that by multiplying?
So the hypotenuse is equal to the short end times the square root of 2. If the short end times the square root of 2 must equal 1, dividing both sides by the square root of 2 to get 1 over the square. Are you talking about how to rationalize? Yeah, multiply by root 2 over root 2. Yep. But again, like, I don't need you to rationalize. If you left things as 1 over root 2, I would not go for it. Okay, so this was, we said 45 degrees. We said our point here was root 2 over 2, root 2 over 2. 45-degree rotation would be how much of a full rotation? 1/8. So what would 1/8 of 2 pi be? Pi over 4. Questions with our quadrant 1? That's all the quadrant 1 information that we need. Those are all of our special triangles. All of what we are going to really be able to get, at least for now. Unit 5 will be able to get some more stuff from this, but for now, this is as far as questions here with our quadrant 1 stuff. How are we feeling? Do you understand where the 1 over root 2 comes from? Solving this equation. Okay, so that's what Emily asked of, like, how do I rationalize this? If you multiply by the square root of 2 on both the top and the bottom, you would get this. But also you can leave it like this. Like if this feels good and you understand this, you can. Just know when I write root 2/2, it's the same thing. Like whichever way is fine. It's just equivalent. And I'm old, so I'm gonna continue to stick with the outdated way. Yeah. Yeah, that has to go. I'm like a billion years old. I've been around since longer than math. That's why I have such a personal hatred for all of these mathematicians, because they got to it first. I had so much longer than that. It's quite great. Not that we're competitive. All right, let's take a look at our other quadrants. If we feel good about this, the other quadrants should be very, very straightforward, because the geometry doesn't change quadrant to quadrant. Now we are going to have to slightly adjust our frame of view when talking about the quadrants. So rather than thinking about how I would get to, say, an angle like this, which is actually going to be the first one that we consider, by starting in my positive x direction and then rotating all the way until I get here, which we could do. There's nothing wrong with that. Let's instead think about starting at my negative x direction and under rotating to get to where we are here. So my halfway mark, my 180 degrees, representing halfway, if I am under rotated by 30 degrees, first and foremost, notice I get the exact same triangle that I get for rotating 30 degrees. If I'm under rotated by 30 degrees, what is my degree measure for what we see here? That would be 150 degrees. And notice again, the triangle is exactly the same. And so what is going to be true about my x length and my y length for a 30-degree under rotation in quadrant 2? Why'd you do negative here, TJ? Okay, so notice we are in quadrant 2. And so my values are going to be the same. X of root 3/2, y of 1/2, but our x needs to be negative and our y needs to be positive. But like exactly the same thing as a 30. Okay, here's where the radians start to be a little bit more helpful, in my opinion. Let's think about this under rotation in terms of radians. Halfway would get us to 1 pi. We want a little bit less than that. In particular, we want to almost hit pi, but we want to be pi/6 short. What is pi minus pi/6? Well, in terms of 6, how many sixths could we represent pi as? Well, after we subtract the 1, absolutely right. So pi would be like 6 pi/6. The 6's would cancel, you would just get pi. And if we are 1 pi/6 short, we would be at 5 pi/6. Notice the ratio of the 5 to 6, a little bit less than 1. We are a little bit less than a halfway rotation. A little bit less than a halfway rotation. We're in quadrant 2. So pi we could think of as like 6 pi/6. And we are pi/6 short of that. So 6 pi/6 minus pi/6, we are at 5 pi/6. Because I'm trying to match to the pi/6 rotation that I am short. Yeah. We'll see that we can do that with the fourths and the thirds as well. And we're about to do that with the fourths and the thirds as well. So this will be like a method that we use. And in fact, let's do that. For our 45-degree angle under rotation, if I am 45 degrees short of 180 of a halfway rotation, what is my angle measure going to be? 135. Okay, what are my X and Y information that normally go with 45 degrees?
I don't know.
√2/2 for both. That's quadrant 1 information. Except what's going to be happening in quadrant 2? The X value is negative. Okay, similar logic to our radians. A full rotation, or to our sixth rather, a half rotation would be like 4π/4. What would be 1π/4 short look like? 3π/4. Exactly. So 135 degrees, or maybe better yet, 3π/4. Again, that over 4 telling us that we're using the same information that we see from π/4 here, and the 3/4, that ratio being a little bit less than 1, telling us that we're in quadrant. Yeah. Sure. Okay. Not going to be long-winded. 60 degrees. What would we expect 60-degree under rotation to look like? 60 degrees short of 180 would be 120. And if we are in terms of π/3, what would almost be a half rotation? 2π/3 is almost a half rotation. And then exact same X and Y information, 1/2 √3/2. But because I am in quadrant 2, -1. Okay, something to note. When I'm closer to my x-axis, notice that my x value is larger. And as we move away from my x-axis, my x value is getting smaller and smaller and smaller. Vice versa with the y-axis. When I'm closer to my y-axis, my y value is larger. And as I move towards the x-axis, my y value gets smaller and smaller. So there are a couple of patterns at play here that we kind of use. The π/3 reference angle is always going to be close to the y-axis. The π/6 reference angle always close to the x-axis. So. All right, similar logic for quadrant 3. Instead of being a little bit of an under rotation from halfway, what are we going to have in quadrant 3? A little bit of an over rotation in quadrant 3. So if I'm 30 degrees over rotated, what is my degree measure going to be? What'll it be? 210. 5π/6 was slightly under rotated. What would slightly over rotated look like? 7π/6. 5/6 was a little bit less than 1. 7/6 is a little bit more.
Wait, how are you figuring out the radian?
5π/6 is a little bit less than half of a rotation, and 7π/6 is a little bit more than half of a rotation. 6/6 would be half of a rotation. Half the circle, yeah.
So,
Because 6π/6 is just pi. Pi is halfway around the circle. So quadrant 2 is a little bit less, 5π/6. Quadrant 3 is a little bit more, 7π/6.
This is like, we're trying to get very close, right? So
So then, yeah, so the 7π/6 here represents the amount of distance that we would travel in order to get here. We could compute that directly. If I did 210 out of 360, you would get 7/12 of the circle. And then you could multiply that by 2π to get the 7π/6. But why do that individually when like we can just look at this 7/6, realize, oh, this is a slightly more than a full rotation, that puts us in quadrant 3. So we could do it directly. I'm not doing it directly because let's just follow the pattern.
Is it like every 15 degrees? It's like,
You'll notice we haven't talked about 15 or 75. That's still okay. There aren't special triangles for 15 or 75. We will be able to talk about it though in unit 5. So say 10. We'll get to those. Yeah.
What do you mean by under rotated and over rotated?
Okay, so we're talking about in reference to going halfway around our circle at the moment. We'll change that reference for quadrant 4, but for now, halfway around the circle. If I'm in quadrant 2, did I make it all the way to halfway around the circle? No, I stopped a little bit short. I'm slightly under rotated. If I make it all the way halfway and then some, slightly over rotated. That ratio is a little bit less than 1 when I'm under rotated, a little bit more than 1. And then to that end, let's actually, before we talk about the XY information, if I'm 45 degrees over rotated, what degree measure am I going to be looking at here? 225 degrees. And if 3 pi over 4 was slightly under rotated, quadrant 2, what would slightly over rotated look like? 5 pi over 4. All right, and then lastly, 60 degrees over rotated is going to look like, shift this ever so slightly, so 225. 5 pi over 4. What is 60 degrees over rotated going to look like? Yeah, kid. Yeah, all based off of what we were doing in quadrant 1. Oh, are you saying based off of like the quadrant 2 stuff? So the pattern that we observed in quadrant 2 is notice that each of these fractions that we get, 5/6, 3/4, 2/3, all of those are a little bit less than 1. What do they all have in common? 5/6, 3/4, 2/3, a little bit less than 1, all a little bit less. In quadrant 3, we pass our 1 pi, we pass 1. So we're a little bit more than, so 7/6, 5/4. What would we expect for our radian measure in terms of pi over 3? If this here was, if under rotated was 2 pi over 3, this is going to be 4 pi over 3 exactly. And then what is the degree measure going to be if we're 60 degrees more? It would be like 240 and 4 pi over 3. That. Okay. Let's fill in the XY information. We're in quadrant 3. What's true about our XY information in quadrant 3? All of them are negative. Everything is negative. And so looking at pi over 6, it's going to be the exact same thing that we have in quadrant 1 for pi over 6, but 7 pi over 6, all of them are going to be negative. So instead of positive √3/2 and positive 1/2, we get negative √3/2 and negative 1/2. Likewise, instead of positive √2/2, positive √2/2, negative √2/2, negative √2/2, and then exact same logic here. Notice it's the exact same information, it's the exact same geometry from our first quadrant. We're in a new location, and so we do something to fit in particular, the x's and the y's are switching. So questions for our first three quadrants? All right, so quadrant one is like standard. That's the one that we have to memorize, and then we're gonna base all the other quadrants off of quadrant one. Quadrant two, we said, was a slight under rotation, a little bit less than pi. Quadrant three was a little bit more than pi. Quadrant four gets it to be a little bit too far away from the negative x-axis to base off of what's going on in terms of a half rotation. But what is quadrant four super, super, super close to being? If we're in quadrant four, then we've almost done what? We've almost done a full 360. We've almost made it all the way around our circle. So if quadrant two was a little bit less than half of a rotation, quadrant four is a little bit less than a full rotation. Okay. So here we saw that all of the ratios were slightly less than 1. What's going to be true about the ratios that we see here? Slightly less than 2. Okay, let's try and apply that logic. Here we are 30 degrees short of a full rotation. If I am 30 degrees short of a full rotation, what is my angle measure? 330 degrees. You'll notice for each of these that I'm starting close to the x-axis and then working my way out. You can do that if you want to. I do not mind. It's just kind of keeping me centered. We're talking about the same reference angle first. Okay. And then in terms of like pi over 6, what is almost 2 pi? 11 pi over 6. That we're almost at that 12 over 6. We're almost at that 2. We're a little bit short. 2 would be 12, a little bit less, we're 11. And what's true in quadrant 4? X is positive, y is negative. Positive root 3 over 2, negative 1 half. Okay, 45 degrees short. What is our angle measure going to be? 315. What would 2 be in terms of fourths? 8 over 4. So if we're a little bit less than that, we're going to be at 7 pi over 4. Almost at 2, not quite at 2. So sad. And then similar information, but again, our y value will be negative. And then lastly, 60 degrees short of a full rotation. If I'm 60 degrees short of a full rotation, I'm at 300 degrees. All right, fantastic. In terms of pi over 3 as what I'm calling my reference angle, the angle I'm referencing in order to figure out what's going on. What would a full rotation be? In terms of like out of 3? 6 out of 3 6/3. And so what is a little bit less than that going to be? 5 pi over 3. How's it going? All right.
Good, how are you?
I'm doing well. And looking at pi over 3, exact same thing, positive x, negative y. As far as like what I recommend in terms of like what to learn here, the reference angles, quadrant 1, that's information to have memorized or to know in some capacity. There are tricks. There's like a hand trick where you can like figure out what's going on in terms of the x coordinate and y coordinate. If you want to look it up, that's totally fine. Your own prerogative. It's actually what I personally use for it to do it quickly. If you kind of want to remember, we're always kind of, as we go from our x's, the x's are kind of decreasing by 1 as we get closer and closer, right? Root 3, root 2, square root of 1 is just 1, but root 1, so on. Whereas the y's are increasing as we go from x-axis to y-axis. Obviously, they'd be doing the opposite if we're going from y-axis to x-axis. Whatever you need to do to learn quadrant 1, and then it's just a matter of being able to identify what quadrant we're in otherwise. So for instance, if I give you 5 pi over 4, to know 5 over 4, a little bit more than 1, quadrant 3, what's going on in quadrant 3? Well, it's going to be exactly like what's going on in pi over 4, but both will be negative.
We can come back on this.
We'll do, yeah, so we've got about 10 minutes left. I want you guys to go ahead and get out your laptops here.